So context switching is not really a part in project one, but it's just explanation of how context switching happens in Pintos so that the implementing Pintos is smoother for you. So this is an overview of what I'll be covering. So I'll be covering process structure, process state, process context, the schedule function, and switch thread. So the process structure is essentially struct thread. Because Pintos, we don't support multi-threading. One process maps to just one thread. So you can just think of one thread as a process. So in thread H, there is the struct thread, and there are these fields. You'll probably adding new fields as you implement the projects, but these are the fields given to you. And process can have 4 states. It can be running, ready, blocked, or dying. So to give you an overview of how processes, the life cycle of a process, when it's created, it should be in the ready state. And if it's selected by the scheduler to occupy CPU time, it should go into running state. And if it finishes execution, then it should exit, which puts them in the dying state. And if it acquires a lock, if it attempts to acquire a lock held by another thread, or if it uses conditional variable to wait for another thread, it goes to the block state. And if that lock is released or it receives a signal through the conditional variable, it should go back to the ready state. And if it was running but it was preempted or it calls thread yield, it should go back to the ready state. So this is the life cycle of a process. So to create a thread, you should use thread create function. What it does is it creates a new kernel thread named name with given priority, which executes function passing aux as the argument and adds it to the ready queue. It returns the thread identifier for the new thread or TID error if creation fails. And in the thread create function, we call init thread, and that's where we allocate memory for the struct thread object with memset. And the template code has 2 lists for managing processes. It has a ready list and the all list. The ready list is a set of threads that are ready for execution, and the all list is a set of all threads in the system. And as you implement project 1, you should be adding more lists, like the blocked list. So this is what happens when you create a thread. So newly created thread is inserted at the line end of the list of all list with using list pushback, and that happens in the init thread portion of thread create. And after the thread is ready, it is inserted into the ready list, and that happens in the thread unblock function. So now I'll move on to the schedule function. Before we move on to the schedule function, any questions about threads or process states? Okay, so if you have any questions, just feel free to interrupt me at any time. So I'll move on and talk about the schedule function. So schedule function, what it does is it schedules a new process. So if you call schedule with the current thread, it gets the currently running process and also gets the next process to run, and it switches context from current thread to next. So who calls schedule? Right now, the template code at thread exit thread block and thread yield, the schedule function should be there. And as you implement more, you should be calling schedule for preemption or when the time quantum, the time allocated to a thread expires. And before calling schedule, you should always disable interrupt and change the state of the running thread from running to something else. Because if you're calling schedule, that thread is yielding its CPU time to another thread, so it shouldn't be in the running state. So as you can see in the template code, schedule is called in the thread block, thread yield, and thread exit functions. So the schedule function looks like this. It gets the current thread, and also the next thread to run. And it checks whether the interrupt is off, whether the current thread is not in thread running state, and the next thread is actually a thread. And if the next thread is not the current thread, it switches threads. And this switch thread function is not implemented in C. You can only see the implementation and assembly in switch.s. So and then it calls thread schedule tail. And today I'll be talking about in detail about what happens in the switch threads function. So before we go on to switch thread function, I'll give you a brief recap of stack. So as you probably all know, stack grows from top to bottom, from high address space to low address space. And RSP for 64-bit, ESP is the stack pointer, so it points to the stack top. And if you push ABC, what it does is it gets the value from ABC and it decrements ESP because stack grows downwards, decrements ESP, and then it stores the value at the address pointed by ESP. And if we call pop ABC, what it does is saves the value at ESP to variable ABC, and then we increase ESP by 4 because stack is reduced. So this is a brief explanation of how stack behaves. So one thing you should be aware of is that there are two types of stacks. So there's the user stack and the kernel stack, and they're different. So they're actually allocated in different physical address space, memory space. So they're different. So if you're executing in user mode, you are using user stack. And if you're executing in the kernel, you are using the kernel stack. So if you say in the user space, you call system call, which is a privileged function, then you enter the kernel. And but what happens when you call system calls is that you switch from user stack to kernel stack, and this also raises the privilege level. And this happens also when there's an exception or when there's an interrupt. So again, going back to schedule. So you call schedule on a running thread, and the schedule yields the CPU to another thread, and the current thread may be going back to the ready state, or it can be going to the block state, or it can be going to the dying state. In any of these cases, you should be calling schedule to yield CPU. So what switch threads does is this. It saves the registers on the kernel stack of the current thread, and it saves the location of the current stack top at the current struct thread stack member, and it restores the new stack top, the kernel stack, into CPU stack pointer, which is ESP, and it restores registers from the stack. So when you call switch threads, the kernel stacks of the two threads should look like something like this. So if we have the current stack, we have the return address, and because we call switch threads with these two arguments, cur and next, by calling convention, the parameters are stored here, next and cur. Actually, cur and next will be the right order, and the ESP points to here, the return address. And we have the register storing the values for the current thread. So switch thread, it does two tasks. It switches the CPU context from cur thread to next thread, and it returns a pointer to the current thread structure. So just before jumping into switch threads, again, we have stack looking like this. So first, you should store the current context, meaning you should store the values of these 4 registers. So you push these register values to the current kernel stack. So you push these values and also decrease the ESP value. So you increment the stack. So that's done with these commands here. And afterwards, we want to store the pointer stack pointer to the thread struct. So how switch thread does that is this. So we get the offset of stack pointer in thread structure. So in the struct thread, if you didn't add anything in between the TID and the stack fields, there should be 24 byte offset between the beginning of struct thread and the stack pointer value field here. So we load the offset to EDX. So if you didn't modify anything, that value should be 24. And we also have to return the location of the current struct thread to EAX. So what you do is, because the current pointer to current thread struct is stored in the stack, you use the you get the pointer from the stack. So so here what we do is we have ESP here, and ESP plus 20 points to the current struct address. So we load that address to EAX here. And if we add the offset of the stack field to the point address of struct thread, we get the pointer to the stack field. So that's storing the, and so that's EAX, EDX, EAX plus EDX. So we're storing the current stack pointer value to the stack field in struct thread of cur at this line. So now we have the stack pointer stored, the current stack pointer stored in the current thread struct. And then to actually begin the switching, we want the ESP to point to the end of the top of the stack of the next stack. So how we do that is following. So again, we have the stack and we have the pointer to the next struct thread in the stack. So we calculate from ESP, it should be plus 24. So we load that pointer value to ECX. And then from that, we load the, because we have the offset from the beginning of struct thread to the field of stack pointer in the EDX. So we add EDX to ECX and load that value to ESP, because that value should be the stack pointer to stack address of the next thread. Yep. So after changing the ESP value, you should also restore the running context of the next thread. So what you do is you pop the register value stored in the next stack to the registers, the appropriate registers. And you do that by just popping the stack in order. So pop EDI, pop ESI, pop EBP, and pop EBX. So that's how we switch threads. So after doing all this, the schedule function calls thread schedule tail. What it does is simple. It marks the new thread as running, and if the previous thread was in the dying state, it also frees the pages allocated to the previous running thread. So as you can see, this part is actually implemented in C. If the current status is, it sets the current thread status as thread running, and if the previous thread is now at thread dying state, it frees the pages allocated to the previous thread. So this is the summary of context switching. So for context switching, the main function we use is schedule. It's called an exit yield and block, and it gets the new process to the CPU. And in context switching, what happens is it saves the context of the current running thread to the stack, and it saves the current stack top at the current running struct thread, and it restores the stack top of the next thread to the ESP register, which is the stack pointer register. And then it also restores the context, the register values from the stack of the next thread to run. And then it changes the state of the next process to running and frees memory from dying process if the previous process was dying. So that's it for context switching. Do you have any questions? Yeah. 50. Yeah. Yeah. They're both kernel stacks of two different threads. So one thread has kernel stack and user stack. So this is kernel thread. This is kernel stack of current stack, and this is this is kernel. This part is a kernel stack of current thread, and this is kernel stack of next thread. So register and register has most likely, yeah, because this is the register values when we were running the current thread, and the screen values are register values when we were running next thread, yeah. So if there are no more questions, I think we can end today's lab session here. Thank you.